name is Silvia Marisel Espinoza. I am PhD student. This dissertation is about carbothermal reduction of mill scale former on steel billets during continuous casting. This dissertation was presented for the International Conference on the Application of the Mossbauer Effect, where this group has presented around 10 research. The project aims to develop new advanced manufacturing technique for the recycling of steel slag. This to improve the quality of lives of low-income residents and preserve the environment. For recycling, the mill scale must be firstly reduced. There is not much information on mill steel scale reduction in the literature. However, it's possible to reduce to iron oxide components, and it occurs from one phase to another, or even simultaneously. For example, the transformation from hematite to magnetite can occur in the same temperature range as the transformation from magnetite to wustite. Similarly, the transformation from magnetite to wustite and wustite to metallic iron, these processes are discussed in depth in this work. Welcome to dissertation. The production process of the steel works in Cedar, Peru, steel plant Chimbote, Peru, consists of several steps, already present by colleagues in previous presentation. One on the last steps includes the continuous casting of the melted steel. The steel previously obtained in a ladle furnace passes from liquid to a solid phase. During the steel cooling by contact with environment and water scale form on the billets surface, which contain wustite, magnetite, and hematite. The molten steel is deposited into copper containers called ingot molds. These molds have square section and are oscillation to avoid the sticking of steel on the walls. Billets are formed and coming out continuously, continuous casting, with high pressure water injection to the fourth phase. This avoids the solidification of the center and prevent liquid from remain during cooking. During the steel cooling by contact with environment and water, scale form on the billet's surface, which contain wustite, magnetite, and hematite. These elements were reported in the Luis Borja research, present maybe one month later. These scales were collected and were crushed until the particle size range in the interval 53 to 600 micrometers. For carbothermal reduction, the sample was mixed were mixed with carbon in a ratio 5:1. That's to say 50 grams iron oxide at 10 grams to carbon in planetary milling ball milling machine for 6 hours. Eventually, the mixing was heated to room temperature heated at 1,200 Celsius. The thermal treatment is very important. This was performed in tubular furnaces in argon atmosphere. The temperature was set from room temperature sorry, and increased 5 Celsius per minute to 500 Celsius. Between 500 Celsius to 800 Celsius, the heating speed was 10 Celsius per minute. Then the velocity between 800 to 1000 Celsius was set 5 Celsius per minute. The temperature was kept at 1000 for 1 hour. The heating continued at 3 Celsius per minute to reach 1140 and kept 1 hour more. Okay, then it was increased at 3 Celsius per minute up to 1200 Celsius and keep this for 2 hours. Eventually, the sample was quenched up to 300 Celsius, which is minus 10 Celsius per minute. From 300 to room temperature, the speed was reduced rate of 3 Celsius per minute. This is very important because in this range occurs the reduction. It's very important, the process, the heating. The literature indicates a reduction process starting with a dense spheres of hematite. An initial reduction with monoxide or H gas produce a layer of magnetite, then outermost layer of wustite is formed, and finally another layer of metallic iron is formed. Iron oxide reduction is a process of removing oxygen from iron mineral in stage. The gas-solid reduction of iron occurs in the following 3 steps. The first step, diffusion of gaseous reduction agent monoxide or H through the gas-solid boundary layers inwards through porous layer of iron, wustite, and magnetite. The reducing agent gas is absorbed in the step 2 on solid surface, and oxygen ions diffuse through the layers to react at the interface. Reduce of all oxides simultaneously at all interface according to the 3 reactions explained above in similar way. Do you see the GIF? Hematite transformed to magnetite, magnetite to wustite, and wustite and iron metallic. Very interesting. The gaseous in the step 3 product talking about the transformation dioxide of carbon or water diffuse of the layer of the porous product. If the layers of the product is dense, the reductibility of the mineral will be poor and will present a minimum speed. This is the literature report about our process. This is the equipment used for the process previously presented by Dr. Shaoli. Okay, this is the most important graphic for the whole paper. The The left graphic shows the thermogram recorded during the carbothermal reduction of the millisteel scale in order to better understand the reduction mechanisms of the ferric oxide components. The figure B showed that this DSC loop in the interval 960 and 1186 Celsius. This is a number very important note, okay? The equipment traces the heating from the room temperature to 1400 Celsius. The thermogravimetric trace corresponding to a line, okay, in the figure A, this figure. Measure the change in mass as a function of the increase the temperature. From room temperature, sorry, my mouse, is uniform above 1100 Celsius, is noted that the weight change in two stages. One, the first loss was this, and is noted by following another small loss between 1100 to 1200 Celsius. This is smaller. The mass loss in each stage were 26.6%. In the total loss, mass loss was around 33. But it's very important to look the process in the each temperature. Okay, let's do it for DCC diagram. Okay, study this temperature in study two processes in the next graphic. Okay, the components of the raw mill scale before carbothermal reduction contain mainly, is reported Luis Borja, wustite together with magnetite and very little hematite. Therefore, during carbothermal reduction process, the first endothermic peak in the DSC plot corresponds to the solid reduction of the oxide contained with carbon. Wustite reduced to iron. Magnetite reduced to wustite, simultaneously at around 1056 Celsius. In addition, during the reduction process, gasification of carbon occurs via boundary, promoting the sudden mass loss. This is the reason. This is 26% mass loss. This is the first. This is hematite at carbon produce magnetite at dioxide of carbon. Magnetite with carbon produce wustite. Wustite at carbon produce iron. Very interesting in this stage, and this is important temperature. 1000, the temperature, repeat, 1056 Celsius. This is the first endothermic peak. The second stage, the DSC loop also showed the second in the endothermic peak around 1158 Celsius. Important temperature. This should correspond to the direct reduction of the wustite produced in the other stage with carbon, which was obtained from the previous reduction of the magnetite. In this stage, less gases than in the previous stage will be formed, which is reflected in a lesser mass loss. This is summary the process. Wustite produce iron, okay, and continue carbon gasification, okay. But this this graphic with a study and the thermodynamic process using the SHOMATE equation. This is graphic do it for the Dr. Cabrera. Is help us do it this explanation and in the paper do it a great analysis. This graph were using the SHOMATE equation. The relationship of these thermodynamic quantities to temperature is shown in the future. The first stage of the reduction will correspond to the equation displayed. Do you see the reaction? Magnetite is about 500 Celsius. The second reaction, wustite, okay, wustite is around, okay, looking, is around 800 Celsius. Is converse, the free Gibbs is negative, okay? Do you look the line when this convert in negative, the system is energonic process, okay? And the last is around, the wustite is around 900 or 850, no? 850 Celsius, respectively, as can be in the future. Okay, using the gift-free energy, and this graph I think is only calculate using SHOMATE equation and the coefficient only using table. It should be noted that relation of the three equations will imply the generation of carbon monoxide and dioxide in the form of gas. This would result in a great loss of mass in the sample, which will be in accordance with the DTA analysis, 1056 Celsius, the first stage. In addition, all three reactions are endothermic, which will explain the first endothermic peak of the DSC analysis. At the point we must assume that three equations are carried out simultaneously, which generates that the first peak of the DSC occurs in a larger than the second peak. The possibility that this reaction occurs simultaneously is reported in the literature. The second stage of the reduction process occurs through wustite at carbon produce iron, okay, plus dioxide of carbon. This reaction is spontaneous at temperature above 1000. It's observed in this is the green about 1000 is spontaneously. And sorry. Is the yellow about this 1000 is observed in this graphic. That reaction is endothermic, and that therefore it will correspond to the second endothermic peak of the DSC curve, 1158 Celsius. In this reaction, a mass loss of the sample is also expected, but not the same extent as in the reaction of the first stage. At the end of this stage, the recovery of iron is complete. The thermodynamic say it's okay, but the experimental, what say about our sample? The X-ray patterns has two patterns with copper and cobalt source of the reduced sample. The diffractograms detect alpha iron and carbon, which demonstrate the reduction of the milliscale. Not X-ray obtained with cobalt radiation, resolve better the iron component that of copper radiation, since in contrast to copper radiation, fluorescent to ionization of the iron atoms is prevented. In fact, X-ray taken with cobalt source also identify magnetite, wustite, and cementite. The patterns of X-ray in future are given in linear and logarithmic scale in order to reveal possible hidden peak. On the left side, the pattern with respect to angle the right is given. On the right side, the pattern with respect displacement, okay, has been plotted. All the standard correspond to the iron power after the reduction, and average particle size was around 400 nanometers is observed. Therefore, carbothermal reduction of iron oxide to alpha iron is demonstrated with both sources. The Mossbauer spectrum obtained for reduced sample is a room temperature is shown in the figure. The fitted parameters and the relative subspectral areas are given in the table. The spectrum was a discrete corresponding sextet to alpha iron structure. Two doublets corresponding to iron 2 and iron 3. Iron 2 and iron 3 assigned to non-stoichiometric wustite phase were elevated at room temperature. Two discrete sextets were adjusted with hyperfile values 49 and 46 Tesla, corresponding to magnetite phase. The relative area ratio within site iron 2 and site iron 3 corresponding is suggestion that is an oxidized magnetite. In addition, a discrete sextet with a hyperfile 20 Tesla It's very short, no? No, it's not this phase, was attributed to cementite structure. All phase revealed by the Mossbauer technique are in agreement with the X-ray diffraction result. Magnetic measurement. The magnetization as a function of the temperature under 500, 5,000 and 10,000 Oster applied felt in the temperature to 5 to 400 Kelvin. Not always magnetic transition is observed in the whole range the temperature. Instead, the loops are horizontal, indicating ferromagnetic alignment belong to alpha iron domains. No paramagnetic signal is detected over the whole interval of temperature, demonstrating to complete reduction of the sample. In the future, the magnetization values increase with applied file. The zero feed cooling and feed cooling loops become reversible since the spin increase alignment, typical from ferromagnetic materials. In the future, magnetization as a function of applied curve are present at 10 Kelvin, 110 Kelvin, and 300. At a high applied, the values of the magnetization remain constant, revealing ferromagnetic alignment of the domains. The presence of paramagnetic domains is discarded or might be minimal since the magnetization does not change with the temperature. The magnetization behavior at low applied fields is better observed in the set feature, revealing a small hysteresis. It's visualized that decrease at the temperature. The coercitivity and remanence increase, this demonstrating the ferromagnetic behavior of sample. Summary. Milliscape sample formed on steel billets during continuous casting have been carbothermally reduced. The initial sample were composed of wustite, magnetite, and hematite. The thermogravimetric analysis showed 2.8 change, okay, between 1,100 to 1,200 Celsius. The true thermal analysis and calculation of the Gibbs free energy and enthalpy change of the reaction, the Carbothelmal reduction process, were assumed to include many reactions. Magnetite to wustite at approximately 500 Celsius. Gasification of carbon at 800 Celsius and wustite to alpha iron at around 850 Celsius. Eventually, at around 1056 Celsius, as upon spontaneous reduction of wustite to alpha irons occurs due to excess of wustite and carbon. The process is reflected in DSC analysis, which show two endothermic peaks, 1056 and 1158 Celsius. X-ray and Mossbauer spectroscopy demonstrate the reduction of the iron oxide contained in the milliscape to alpha iron. This is also reflected in the magnetization measurement of the reduced sample, where the ferromagnetic state belonging to the alpha iron domain is verified. Thank you very much. I appreciate CONCYTEC, Fondesit, and the World Bank because accompany this project, and this is the reference I uses in the paper and this presentation. This is the poster, very, very nice, presented in the event. Okay, it's all. Thank you.
Thank you very much. Thank you very much, Marisel Espinoza Suarez. Now it's time for the questions. Narciboya, do you have any question? Narciboya? Narci, are you there?
Yes, sir. Yes, sir. So you are giving carbothermal reduction. In that case, so 1 hour and 2 hours. So while increasing the temperature, so what are the components? It is reduction or decompose. And finally it is graph, it is reduced. So tell me what is the reason?
That is a several step, and the carbon added is very, very important, and the oxygen is very interesting. This is process described in the literature and do it in the our process. It's confirmed in our process. I do it thermodynamic and using gives free energy and say it's okay. It's okay. The reduction is the temperature is okay, and prove the experimental.
Okay.
Yeah, but show that.
Okay.
This is your topic, no?
Yeah, it is. Okay.
Yeah.
So what are the components? It's reduction or decompose. So whether it is possible to identify compounds?
Sorry.
So whether it is possible to identify what are the components, reduction or decompose?
Yes, it's possible reduction, but I think maybe use more time for the reduction all this sample, because the finally and the experimental have boostite and have magnetite and cementite. Maybe transfer all in alpha iron maybe needs more time, I think, but you are a specialist.
Okay, thank you.
Thank you, Narciboya. Marlon, any question?
No question.
Okay, I have a question, Marisel. Can you show your thermal curve, please? The thermogravimetric.
Yeah.
Yeah, there. Well, can you zoom in, please, on the left plot? On the left. Let's focus on the left. Can you make this much bigger, please?
No.
The left one.
I can do it. Okay.
Just zooming in. Without presentation, you can zoom in.
Yeah.
Excellent. That's good. Thank you. Yeah.